So here we're told that each capacitor in the combination shown below has a breakdown voltage of 15 volts. We want to know what is the breakdown voltage of the combination between points A here and B here. The first thing we're going to do is reduce this to a situation where here, well, these are in parallel, so we know C equivalent is equal to 20 microfarads plus 20 microfarads. Same thing goes for this one here. So then we can redraw this and say, well, this has 40 microfarads on it. This has 10 microfarads on it. And this one has 40 microfarads on it. And we want to know what is the breakdown voltage between this point and this point. We're going to call this point A, this point B, and this point C, and this point D, just so that we can separate all of these capacitors. Now, we know that if we have a charge Q that enters here, this plate here has the same charge Q on it, as does this one, as does this one. So Q on this plate is the same as Q on this plate, is the same as this Q on this plate, because, well, the charge is literally just going to be equivalent everywhere around because it's in series, and we know that. So then we can write out that Q is equal to the capacitance, so 40.0 microfarads, times delta V AB. What I'm saying is that the charge on this capacitor here is its capacitance times, well, what is the voltage difference across the capacitor plates? Well, that's the delta V between points A and B. And we know that because Q is all the same, that's going to be equal to 10 microfarads times delta V BC. So for this one, it has a certain amount of charge on it. And then we have the potential difference between B and C. And that is going to be equal to 40 microfarads times delta V CD. Same thing, right? Potential difference between this plate is, well, what was the potential here? And what's the potential here? That's going to be our difference. Now, because we know that, we can rearrange some things. This is 40, 10, 40. We can all divide it by 10, and we get 4 times delta VAB is equal to 10 times delta VBC is equal to, sorry, not 10. We divided by 10. Divided by delta VBC equal to 4 delta VCD. So because we know this, we can just divide all these equations by 10 microfarads, and then we get this here. Now this is just the relationship between the delta V, so the potential difference between the three plates. Now we know that when delta V is bigger or equal to 15 volts, we know that delta VBC breaks down. Okay? And the idea here is that, well, we were told, right? We were told at the beginning that each and every one of them has a voltage breakdown or breakdown voltage of 15 volts. So when we get 15 volts, this guy is going to go first. And the reason for that is because delta V across AB is going to be a quarter of that across BC. So we know that when delta V is bigger than or equal to 15 volts, delta V BC breaks down. And then we know that at that point, delta VAB is equal to delta VCD. So at this breakdown point, so this is the breakdown. When this happens, we want to know, well, what was delta V across A and B, and what was delta V across C and D? And we know that that is going to be equal to 1/4 of delta VBC. And we know that at this breakdown point, that was equal to 1/4 of 15 volts. So as soon as we hit 15 volts, there's breakdown. We have an electric potential difference across this plate and across this plate. What is it? Well, it's 1/4 of 15 volts. So delta VAB is equal to delta VCD is equal to 3.75 volts. Now, we want to know what is the breakdown voltage of the combination. So we're just going to be adding up all of our potential difference across this one, and this one at the point of the breakdown. So we're going to add that all up. So V from A to D which is what we want, is equal to V from A to B plus V from B to C plus V from C to D, and that's going to be 3.75 volts plus 15 volts plus 3.75 volts is equal to 22.5 volts, and that is our final answer.